Did everybody get a packet? Got your name on it? All right. So chapter 4 is trigonometric functions. And yeah, I always like the way that sounds when you say it, trigonometric. It's one of those fun words to say. Trigonometric functions have to do with basically sound waves is where we use this the most. So it says when the motion of an object causes air molecules to vibrate, we hear a sound. Kind of cool to think what we're really hearing is the vibration of air molecules that our ear captures. We measure sound according to its pitch and loudness, which are attributes associated with the frequency and amplitude of a sound wave. As we shall see, it is the branch of mathematics called trigonometry that enables us to analyze waves of all kinds. Indeed, that is only one application of this powerful analytical tool, and then it says we've got more applications later on. One of the coolest applications that I see for sound waves is recycling. My husband works at Great River Energy, and one of the things they do is they separate everybody's garbage into burnable piles. Believe it or not, at this age, some people still don't do recycling at their houses. They put everything in the garbage. So what they have is a series of fans that blow out anything that's burnable from the garbage so it can go to Great River Energy and be burnt. Problem: aluminum is not something they can get out with a magnet. There's a lot of metals they can get out with a magnet system, but aluminum is not one of them. So when people throw a can in the normal garbage, for years it was, how are we going to separate this out? I mean, it's worth something. It's recyclable. We can actually get paid for getting people's cans out of the garbage. And what they found out was sound waves work for that. And so as the garbage goes through the plant, it goes through the systems of blowers, the systems of magnets, and eventually sound waves will hit the aluminum. And when they hit the aluminum, it pings the cans up into the air, and they get caught by a net so they can get recycled. So there are all kinds of applications that we have for sound waves that are things we wouldn't normally think about. Another one that's just kind of interesting, because I have a lot of animals, is they're trying to figure out how elephants speak to one another. And when people stand near elephants, it's not like you can hear the noise. It's at a frequency that's really hard for humans to catch. But they totally believe that elephants speak to each other. And so the sound wave study that they have there is trying to help them get that piece. So what to expect in Chapter 4. Trigonometric functions describe the ratio of two sides of a right triangle, regardless of the size of the triangle. You guys remember back in geometry, SOHCAHTOA, we use that. I have a little jail over here that I'm going to bring up right now because I see some people with their phones out. This is my cell phone jail right here. I should not see phones being used when we are going over stuff in class. You need to have a commitment to the material just like I do to teach it. So the compilation of these numbers allowed the progression of many topics in mathematics. Who would have thought that the first trigonometric tables would help enable us to store sound waves digitally on a compact disc? The study of trigonometry has been here for thousands of years. Thousands. They knew what it was, but they never would have imagined that we would use it for CDs. What they were using it for was building. I mean, this was in engineering that they used trigonometry. The study of trigonometry, both historic and essential as we go towards calculus. We already learned in Chapter 5 that while there are ways for us to take roots and get answers, when we deal with those in calculus, it is often better to take the natural logarithm because of the way it works with calculus. Same thing here, and we're going to have to go a little past what we knew in geometry if we're going to be able to understand calculus. Angles and their measures. We're going to get into that a little bit today. Pardon me. Trigonometric functions of acute angles, trigonometry extended, the circular functions, we'll start talking about that today as well. Graphs of sine and cosine and the sinusoids, that'll take us a little while to get to in this chapter. Graphs of tangent, cotangent, secant, and cosecant. And then we have inverse trig functions and solving problems with trigonometry. Now, solving problems with trigonometry pretty much going to be throughout everything we do. There's word problems with every section that we're going to go through. So the first thing we have to do is get ourselves back into thinking about trig. And a little of the history helps us with that because it's kind of like, why did this all even come into being? back in high school, we did not have graphing calculators. We didn't have any calculators at all. So our pre-calculus book had about 100 pages in the back that had all of the sine, cosine, and tangents of relevant acute angles. And this is something they've been trying to figure out for thousands of years. So Hipparchus of Nicaea, the father of trigonometry, compiled the first trigonometric tables to simplify the study of astronomy more than 2,000 years ago. Today, that same mathematics enables us to store sound waves digitally on a compact disc, or for most people right now, even just to download them. Hipparchus wrote during the 2nd century BCE, but he was not the first mathematician to do trigonometry. That happens quite a bit. You know, somebody finds somebody else's work and then they keep going on it. Greek mathematicians like Hippocrates of, I don't know if that's Koi or Choi, and another name I don't want to try and pronounce, I do know that's Cyrene, had paved the way for using triangle ratios in astronomy, and those same triangle ratios had been used by Egyptian and Babylonian engineers at least 4,000 years earlier. The term trigonometry itself emerged in the 16th century, although it derives from ancient Greek roots, where we have tri as 3, bonos as side, and metros as measure. So, how did it really come to be? The stars. At that point, they were always thinking about, lack of a better word, a higher power, God. They were looking at the stars and they wanted to figure out just how everything worked. And it had to do also with navigation whenever they were going out on the seas. And so, out of necessity, trying to find their way to places, they started to study astronomy, which in turn helped them get into trigonometry. So the Babylonians are thought to have developed the first number system, which was a base 60 system. Seems like a lot of history about math, but this is really important because that base 60 system is what told us there are 360 degrees in a full circle. And they lived in Mesopotamia, which is thought to be a portion of modern-day Iraq. So a base 60 system. Now, the reason I'm putting that up there is because our system is a base 10 system. And we start with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's base 10. And then we just repeat. So we say, well, what's 10 plus 1? That's 11. What's 10 plus 2? That's 12. So our base is tens in our system. Theirs was 60. So they had enough symbols to separate the first 60 numbers from each other before they did any repetition. It was a really complicated mathematical system, but it did put us on the right path as far as 360 degrees. You know, from trigonometry, degrees are not the best way to measure angles. They're not, but they're the easiest one, and that all comes from that base 60 system. So the idea of dividing a circle into 360 equal pieces dates back to a sexagesimal 60-based counting system of the ancient Sumerians. The appeal of 60 was that it was evenly divisible by so many numbers. It had a lot of factors, and so they thought there's got to be a lot of good math that we can do with this. Early astronomical calculations wedded the sexagesimal system to circles, and the rest is history. So degrees, first most basic way to measure an angle. And from there, we got more specific. So review from geometry. An angle in standard position has its initial ray on the positive x-axis. So let's make a drawing. All right, positive x-axis. There it is right there. That's going to be the initial ray for all of our angles. And that is too small. We start on that positive x-axis. Now, if it doesn't go anywhere, then it's 0 degrees. But usually what we'll do is we'll use another ray to form an angle, and that one is called the terminal ray. The terminal ray can land anywhere. So I will just put my terminal ray right here. Counterclockwise is considered a positive angle movement. And I know that seems really weird to us, but you have to remember most of this came from Middle East, parts of Europe, and everything is backwards over there as far as that goes. So a counterclockwise rotation results in a positive angle, like it says. This is why the quadrants are numbered the way they are. First, second, third, and fourth. So positive counterclockwise. Clockwise rotation results in a negative angle. And like it says, we use such Greek letters. A lot of times we just use theta. That's this first one here. Oh, let me move this up. Theta, phi, more often used in calculus and AP stats. Alpha, beta, and one other one you're going to see from this book will be gamma. And those are just Greek symbols that stand for, this is the angle we want to focus on, right here. So theta, phi, alpha, beta, gamma. Now, I should mention, a lot of people just pronounce that one pi. But I don't want to confuse anybody with pi and phi right now, so I'm going to say that as phi. The pictures below show some angles that are in standard position. What are some plausible angle measures for each? Okay, it's time to review the geometry. A straight angle is 180. That perfect 90-degree angle is what we have with our x and y axis. So they're asking us to just say, okay, if we had to take a guess, we don't have a protractor here, what do we think this would be? So, yeah, it kind of looks like 45, doesn't it? Should we put a negative in front of it? No, this one is counterclockwise. You can see by the little arrow. That's why the little arrow is important. So about 45 degrees. But while we're at it, we better remember a little bit more, because remember, degrees are the least specific way to measure an angle. Radians are a much more accurate way. And you dealt with radians just a little bit in geometry, so you might have forgotten how to convert degrees into radians. What we do is we multiply by pi over 180 to convert to radians. Pi over 180 to convert to radians. Too many t's. So if we have pi over 180, and originally it was 45 degrees, we're going to take 45, might as well slap a 1 over it, because when you're working with fractions, it's usually helpful to have everything as a fraction. And then we have to think, how many 45s would go into 180? How many 45s? 4 of them? Everybody? Okay, I want to make sure everybody's doing the math in their noggin. So that would give us pi over 4. So this is 45 degrees, but it is also pi over 4 in radians. Now, radians technically don't have a label, but we need to know, hey, if it has pi in it, we're talking about radians. Or if there's not a label, it's radians. So let's look at this next one. This one's kind of interesting, isn't it? All right, well, let's see. It's going this way. That was 90. That's 180. How much more do you think this is? Here to here. Kind of look like 45 again? Okay, so 180 plus 45. What do you get? 225. But what's unique about this one? It is negative. We're going clockwise with this one. So now if we need that in radians, we're going to have to do a little negative 225 over 1 times pi over 180. And now if you get sick of doing all the reducing in your head, remember you can just do that with your graphing calculator as well. Just get it in as a fraction, so negative 225 divided by 180. Math number 1. There it is, negative 5 pi over 4. But the negative is important because it tells us the direction. So, like I said, if you don't want to reduce in your head, don't reduce in your head. Use the graphing calculator to do that. Whoa, look at the third one. What's unique about that one? more than one full rotation, right? Positive or negative? Positive. We're starting here on the x-axis and we're going counterclockwise. Looks like a 45-degree angle again, right? From the x-axis up here, so it's 360 plus 45. So about 405 degrees. Did you already do the radians? What you got? 9 pi over 4? All right. Looking goofy in that last one too. Obviously more than one rotation, so let's see how much more. So from here around 360, we've got 90, 180, and again, it looks like we're splitting it with that 45, so 225, 360 plus 225. Positive or negative? Positive, going counterclockwise, okay? Go ahead and get me that in radians, please. 13 pi over 4. So the degrees came from that sexagesimal system, but eventually they figured out more math, more and more accurate math, and that's where the radians come from. Because with circles, we know pi is inherent. It's in every formula that you talk about when you're trying to figure out stuff with circles. Circumference equals 2 pi r. Area equals pi r squared. It's a part of it, and radians give us that. So down here, they're saying, all right, smarty pants, you did those problems. Now let's see if you can draw them. We know where they're supposed to start, right? Where do they start? Positive x-axis. And if you think in terms of 90s, it generally helps you. Now this one's positive, so I've got to put my little arrow eventually and say, well, there's 90, there's 180. Ooh, I've got to go 10 degrees more. That should do it. And I'm just going to put that little 10 degrees there because if somebody's grading my paper, I want them to know, hey, I knew that was 10 more degrees than 180. They'll be able to see it from there. And again, this arrow to show I was going counterclockwise as I go through it. Oh, we better put the name of the angle on it. This was theta. All right, we've got a beta. Which way are we going this time? Clockwise. All right, well, let's see how far we can get. There's 90, there's 180, there's 270, and just a little bit more. How much little bit more? 6 degrees, a little bit more. And this is beta, right there. Smartboard makes it hard to draw that little arrow there. So it's showing that clockwise movement that gets us the negative. Alrighty. Clockwise or counterclockwise on 91, negative 91 degrees. Clockwise. There's 90 and a little bit more. How much is the little bit? 1 degree. And since that's going to be really hard to fit in there, I just wrote it down here with an arrow. And that is 5. Right there. Then, 629 degrees. Clockwise or counterclockwise? Counterclockwise. And this would be a spot where I would stop and say, okay, obviously that's more than 360. How much more than 360? So you take 629 and you subtract 360 and you see how much more. So we have to go one full rotation, and then we have to go another 269 degrees. So 90, 180, but not all the way to 270. And with this one, again, I might just go ahead and put a little arrow and say 1 degree right there so that people know how short that was. And that is alpha. 1,822. Seriously. Going around definitely more than once, right? So we try to figure out, well, how many times? Well, let's see. Let's divide. So 5 and some change. So we're going to have to go 5 times. And I want to know, well, how much more? Well, 360 times 5 is 1,800. This is 1,822. 22 degrees more. So this is where we want to start with little ringlets inside and work our way out as far as we can. 1, 2, 3, 4, 5, and another 22 degrees, which I know I made way too big. So I label it. And I put my table here. Oh, look what they did with gamma. Well, first of all, clockwise or counterclockwise? Clockwise. How many times? 160? Wowie. So we got to go around this thing 160 times, and then we'll have a little change. Let's see how much change. 160 times 360. 31 extra degrees, right? So here's what we're going to have to do with this one. We're going to have to do something like this that just shows, hey, we were going this way. And then up here, make a little key for it where we say equals 160 times. Because nobody would be able to tell we were drawing that 160 times. It'd just be a big mess. And then like we said, if we went exactly 160 times, we'd be at 57,600. So we need to go another 31 degrees. And that is gamma. Okay. So notice little extra things so that if somebody's grading my paper, they know, hey, they knew exactly what they were doing. You know, I can see the numbers here that would help finish this up for me to know that they have this absolutely right. So now we've done a little bit with radians and we've done a little bit with degrees and the drawing. We haven't done any drawing with radians. Probably won't get to that today. But part of our objective was just seeing, can we draw these angles? And notice, in example 3, phi at -91 and alpha at 629 share a terminal ray. Let's go back and take a peek. So that one and this one. The green angle over here and this one. What does that mean to us? We always want to use the easier of those two, but we tend to want to use those that are positive. So if we had a choice between these two, we actually wouldn't use -91 nor 629. We would use 269 because that would be the smallest positive angle possible that could represent that same terminal ray. And what they're getting at here is there is a special name for that relationship, and those are called coterminal. That's another little something that you had in geometry. So those two angles shared a terminal ray, although the angles are not equal, but they represent the same terminal ray. We could say that they are coterminal. So two angles are coterminal with each other if they share that terminal ray. In general, any given angle theta, its coterminal angle will be written as theta COT in subtext. It's kind of small in your notes there, so just make it a little bigger. And how we get to those, if the information is in degrees, is we just add and subtract multiples of 360. That's all we do. It's got to land in the same spot. So it's got to go all the way around and land right there. Now this thing sometimes messes with people because that's a new notation for us. That means n is in the set of numbers, and z, way back at the beginning of the year, that we used to talk about the integers. So this means subset of, and then z is the integers. So they're saying if you want a coterminal angle, you could add 360 times 1. You could add 360 times 2. You could add 360 times 3. But if you needed to, if you needed negative angles, you could do 360 times negative 1, 360 times negative 2, and just use the integers to get that. So in example 4, it says, if theta is 465, find all the angles theta coterminal between, be specific here, 0 is in the middle, or not, theta is in the middle, and we have 1,000 and negative 1,000. So 465 degrees. I don't know about you, but, oh, are we getting close? That makes me worried. 49? Okay, we can do this, because we're just adding and subtracting 360. So 465 plus 360, 825. Plus 360. Oops, we're over. So it said we had to be between 1,000 and negative 1,000. Well, that means I've got to go the other way. So 465 minus 360 is 105. And I should put the correct notation here. Theta COT equals 105. You suppose that's all the negatives that are coterminal? No, keep going. Minus 360. Theta coterminal, negative 255 degrees. Another one. Keep going. Negative 360. Theta coterminal equals negative 615 degrees. And make sure you put the little bubble for degrees on there. You think we can get another one in? One more. Negative 975. And then for certain we'll be outside that negative 1,000 to 1,000 restriction that they had up there. Of all of these, which would be the one we would want to work with? Exactly. Smallest positive is what we would want to work with. All of the values for trig would be the same for all of these. They're not the same angle, but all the values for the trigonometry for these would all end up being the same. So on the next page, we have this. For each angle, phi, find the angle theta coterminal with phi such that our angle is between 0 and 360 degrees. That's where we're going to have to start tomorrow. You know what? Do those two for part of your homework. We're not going to have a lot. And I have a worksheet. Bad news, you won't be able to do the whole thing. I know. I promise I'll make it up to you.